from Math130 are going to be talking about trigonometry. So first of all, I'm going to be the cameraman and the editor. That's going to be me. So today James is going to give us a brief history of Pythagoras and trigonometry. My good friend Rodney is going to be giving us some explanation of trig with some Pythagorean identities. And to finish us off, Randy's going to show us some real world applications of trigonometry. So I'll be behind the camera now. Enjoy our podcast.
Hello everyone, and I will be talking about the history of Pythagoras. Now, who was Pythagoras? We know that the great Pythagoras of Samos was a very enigmatic figure. Was he a mathematician, an astronomer, or was he a falsifier of information and beliefs, or just plain ludicrous and crazy? So today we will be talking about the mathematical side of Pythagoras. So, Pythagoras reportedly learned from the ancient Egyptians the applications of geometry, since geometry was a very important part of how they could measure the land of Egypt at the time. So, with his knowledge of astronomy, Pythagoras took geometry, arithmetic, and astronomy and combined them together to create the study of trigonometry, which we will be taking a look at. Also, Rodney will be discussing the trigonometric identities of c squared equals a squared plus b squared, as well as sine squared theta plus cos squared theta equals 1. And now on to you, Rodney.
Sorry that this circle is not perfect, but I'm a mathematician, not a bloody art student. So, what is a unit circle? A unit circle is a generic circle with a radius of 1. As you can see, radius of 1. Doesn't matter the scaling, it's always 1. This whole measurement in a whole radian length is 2 pi, and radians is measured by an angle subtended by an arc length, where an arc length of a circle is the same as circumference, where circumference of a circle is equals to 2 pi. Therefore, a full rotation of a circle is also equals to 2 pi in radian measures. Okay, so this is our theta, but for explanation purposes, I'm going to show you using one in the first quadrant, which I'll just quickly draw up now. Point here, this point is given, the x-coordinate of this point is given as cos any angle. For this example, it would be cos alpha, and the y point for this point here on this triangle would be given as sine alpha. So sine is the opposite, which will be given as a, because it's our unknown, over our hypotenuse, which is 1, because 1 is our radius in our unit circle. So sine a, which is your opposite, over your hypotenuse is equals to sine theta. Now, assuming we know sine theta, we can now cross multiply. So now we can say a is equals to sine alpha, I shouldn't say theta, multiplied by 1. Therefore, a is equals to sine alpha, proving that we can actually get that point there using that. Now for cos alpha. So cos alpha will be given as adjacent over hypotenuse, where your adjacent is now unknown, so we'll put that as a b. So now we'll go cos alpha is equals to the opposite, the adjacent, which is b, over the hypotenuse, which is 1. So now we can simply multiply it by cross multiply to whatever you got, and we'll get b is equals to cos alpha times it by 1, which is just, therefore b is the same as cos alpha. As my good friend James said before about sine squared plus cos squared equals 1, let's go do that. Now, let's prove it. Let's move over to my unit circle. Now, as I was stating before, this point here is my x, on respect to my x coordinate. And my y coordinate. Now, this is a right angle, Now let's go use basic Pythagoras, which is c squared is equals to a squared plus b squared, where c squared is 1. So now we'll just substitute, so c is equals to 1, a is equals to cos theta, because cos theta is the x distance from 0 to our point, and b we'll put as sine theta, which is from 0 to our sine theta, which is a distance. Now we'll substitute. So now we'll go 1 squared is equals to cos squared theta plus sine squared theta, where 1 squared is 1. So we've got, I'm actually going to flip it just so I can actually prove to relate it back to what I wrote before. So I'm actually going to rewrite it. So sine squared theta plus cos squared theta is equals to 1. Help linking this point to my basic foundational point, which is that. Now I'm going to show you one more Pythagorean identity which will prove that tan squared theta is equals to 1 plus cot squared theta. Okay, let's go. So we'll divide the whole lot by cos squared alpha. So now cos squared alpha over cos squared alpha will cancel and give us 1. Sine squared alpha over cos squared alpha is the same as tan squared alpha. And come over here, 1 over cos squared alpha is the same as sec squared alpha. Now let's just put these down. So now we've got tan squared alpha plus 1 is equals to sec squared alpha. Let's deduct 1. Deduct 1. Therefore, tan squared alpha is equals to sec squared alpha minus 1, which is another identity. When did you guys get back here? Let's just clean the board. Okay, now we're going to talk about the real-world applications with Randy.
Okay, so my name is Randy, and I'll be talking about the real-life application of trigonometry. So trigonometry, one of its most obvious application being to measure length or distance. So for example, in order to measure the height of a mountain, an observer will use an inclinometer, which looks like this, to measure the angle of his line of sight from his position at the bottom of the mountain to the top of the mountain at 2 different locations, which looks like this picture over here, on the same axis, and then calculate the height of the mountain from the gathered numbers using simple trigonometry formula. An interesting application of trigonometry in the ancient times was the invention of sundial, which looks like this. So sundials can tell time depending on the position of the sun relative to Earth, as long as the sun is visible from where the sundial is located. In physics, trigonometry can be used to determine the degree of curvature on roads and railroads, to make sure that no car and trains would go off the road or the railroad when turning at high speed due to centripetal force. It's very dangerous if this calculation can go wrong. So trigonometry is also used as the base concept of the longitude and latitude lines, as we know that we use in the globe. With longitude and latitude lines, we can tell where exactly we are located on the Earth, determine the climate of a place, and tell the time difference between cities. This concept is used to create the navigational system known as GPS, which has been widely used ever since the invention of smartphones. And that's it from me. Thank you very much for watching our podcast. So here we are, in the conclusion of our podcast, with me in front of the camera. I guess you could say we've made a full unit circle, coming back to where we started. I've got James, Randy here, Rodney behind the camera. I hope you've enjoyed our podcast. So this is me, signing off. Because